Okay, so I checked, and well, 2-minute search didn't tell me what the best case running time of Polyamore was, but actually I could figure it out because the worst case running time is also linear. This is not so easy. You need certain tricks. The original implementation was worse than this in the worst case, but using the Galil rule and stuff like that, which we don't worry about in this course, you can get it down to linear worst case. And if this is linear, then this is the best case is m plus n over m. Notice, so this is better in the best case than these two. And actually, in practice, it is faster. So now, let's talk about Karp-Rabin, which is also going to be linear, but is super cool. But in order for it to be more understandable, I'm going to change this example from being a letters to being numbers. So let's just say that we're going to map A to 0, B to 1, D to 2, L to 3, A 0, B 1, D is 2, L is 3, and I think R is 4. Okay, is that all of the characters? Yes. So now P is 0, 3, 0, and T is 0, 3, 0. 1, 0, 4, 0, 3, 0, 0, 3, 0, 1, 0, 4, 2, 0. Okay? Or this goes in here. Okay, so now I'm looking for 0, 3, 0 in this string, which is the same thing. I haven't really done anything. So why does this help? Well, because Karp-Rabin uses hashing on numbers. Okay, so it uses a bit of number theory. And so it's just easier to think about if this is actually a number. So what are we going to... We're going to do something that's quite a lot like the naive algorithm, but this is going to, as long as this is short, it's a number, we can compare two numbers really easily, whereas we can't compare two strings really easily. So actually, I mean, it's true, everything is a number. In a computer, everything is a number. I mean, it's this a sequence of bytes. So a string is actually a number in base 256. All of the bytes are digits between 0 and 255. It's like a hexadecimal number is a sequence of digits between 0 and 15. A decimal number is a sequence of digits between 0 and 9. So I'm really not changing anything. I'm just putting this into decimal, whereas here it's actually if these are ASCII strings, it's in base 255. And in fact, anything in the computer is a sequence of bytes, so it doesn't really matter. So what is the idea? Well, we're going to take a sliding window. It's the same as the naive algorithm. Maybe I should actually shift this over so I can get, yeah, let's squeeze this in here. For 0, this is 4, 0, 3, 0, 0, 3, 0, 1, 0, 4, 2, 0. Okay, so now we've squeezed it. The idea is to take a sliding window. So take some little chart and say, okay, is 030 the same as 030? So these are small numbers. If we have them stored as integers, then we can do this comparison quickly. As long as this is pretty small, we can do this comparison in constant time. We slide it over, is 301. So before with the naive algorithm, we were saying is 0, if we were doing naive, we were doing comparing 0 and 0, and 3 and 3 and 3, and 0 and 0. So that's like how we would do it. People, if we were comparing numbers, we compare digit by digit. But on a computer, on a RAM, as long as the numbers are small enough to fit in one machine word, you can do these comparisons in constant time. So is 030 the same as 030? Well, yes. So we output 1. Okay. Is 301 the same as 030? No. 010 same as 030? No. 104 the same as 030? No. 040? No. 403? No. 030? Oh, yes. So that comes back yes. So we output this position, which is 7. 1, 2, 3, 4, 5, 6, 7. 300? No. 003? No. 030? Yes. 301? No. 010? No. 104? No. 042? No. 420? No. So that's leaving, if the pattern is small enough that when you view it as a number, it fits into a constant number of machine words. So you actually can take the number, take the string, and cast it as a 64, 128-bit integer, then you're fine. You can just, how do you do this sliding along? Well, notice that when I do this sliding along, we can actually, if we have the, say you have some number here, and now you want to change it, you want to change it from 104 to 040. What are we actually doing? Well, to map from 104 to 040, well, this is 1 times 100 plus 0 times 10 plus 4 times 1. And this is 0 times 100 plus 4 times 10 plus 0 times 1. Well, what we can do is just knock off the first thing. So we subtract the value represented by the, in this case, 100, multiply everything by 10, and then add what's in the ones place. This one actually wasn't a great example. But say we want, where's something more interesting? Unfortunately, everything has A's in here. So there are all these zeros. But say we wanted to go, so let's put something a bit more interesting. 6, 4, 3, 7, 9, 1, 5, 4, 2, 8, 2. We want to go from, let's say that we look at this number, and now we want to go to this number. What do we do? Well, this is 4 times 100,000, 1, 2, 3, plus 3 times 10,000, plus 7 times 1,000, plus 9 times 100, plus 1 times 10, plus 5 times 1. This is 3 times, so if this one is x, and this one is y, 3 times 100,000, and 7 times 10,000, and 9 times 1,000, and 1 times 100, 100, and 5 times 10, no wait, what? I've lost one. 100,000, 10,000, 1,000. 7 times 10,000, 9 times 1,000, 5. Oh, wait, yeah, this goes up. This is here. It doesn't include the 2. 5 times 10, 4 times 1. Okay, so x is this, y is this. To get y from x, we don't have to do all these multiplications and additions again. We can just say that y equals x minus 4 times 100,000, right? And then all times 10, and then plus 4. Okay, so everything gets shifted to gets increased by 10. It sort of gets shifted left 1 in our decimal representation, and then we add the ones. So we knock off the thing on the left, we shift, we increase the magnitudes, and then we add the ones. Okay, so this is a constant number of arithmetic operations. So as long as the numbers fit in a constant number of machine words, we can do it in constant time. So that's why, and then we can do the comparison. As long as the numbers are not too big, we can do the comparisons in constant time. And so we've sort of changed the naive algorithm by viewing things as numbers and doing hashing so that it runs in linear time. But that relies on the numbers not being too big, right? So we can deal with it if each character is 8 bits, so we can quite easily deal on a modern computer. You can deal with 128 bits, which is 16 times 8. Yeah, I think 64. Yeah, okay. So we can deal with a pattern of 16 characters on a normal computer. But that's not very long, okay? I mean, 16 characters, what if you want to look for a pattern that's 20 characters or 50 characters or something like that? Then this breaks down. Then it, like doing this check piece by piece, it would turn back into the naive algorithm. It would be a little bit faster in practice, but it wouldn't actually save you. So, but we haven't used the hashing yet. So what do we actually do? Well, I hope you have seen modular arithmetic. This is why it's such a pain teaching with nobody there. I can't ask, has anybody seen modular arithmetic? I hope you, so I hope you understand this stuff. The idea is we do everything but modulo a randomly chosen prime. Okay, so suppose that we have 64-bit words, okay, machine words. So we can deal with numbers up to size 2 to the 64 minus 1, but we don't want to deal with numbers bigger than that. So that would actually limit us to patterns of length 8 unless we do this hashing. So what are we going to do? Same thing, but we're going to take everything modulo this prime. How do we choose this prime? Well, we choose this prime pseudo-randomly in the range up to from 2 to 2 to the 64 minus 1. Okay, and there are fast ways to choose primes in that range. And so this is going to give us some prime p. Okay. So we have 64-bit machine words. We choose a prime P in the range. So actually so it's going to be 0 to 2 to the 64, but this is going to, so this one, it includes 0. Actually can't include 0 because 0 is not a prime, but we're going to include it in this range, so it's open at this end, so it doesn't actually include 2 to the 64, so it actually goes to 2 to the 64 minus 1. And then we do everything mod P. Okay, so doing this mod P is going to mean that our numbers never get too big. I mean, okay, if we're careless, then we might actually need 2 machine words in when things get a little bit too big, but then it'll get small again when we take everything mod P. Can I give you a good example of this in a reasonable amount of time and board space? Maybe I'll do an example at the end. So you have your sliding window here. Let's say that our pattern is a bit longer. Ignore what the pattern is. So you have the pattern is some number modulo P, so it fits in one machine word. So you don't remember the pattern. Well, you do, but what you're thinking about is that number. So the pattern is a number modulo P. And now, whenever you slide the window along, so remember you knock off the first one by doing a subtraction, and then you multiply by 10, and then you add the next digit, and then you do mod P. So to make sure that nothing gets too big. And because if you had like lots of zeros and stuff like that, then if you're adding non-zeros at the end, it might get over P. So you're keeping this sliding window, you're having the sliding window modulo P. Sliding window is a number modulo P. And then whenever this is equal to the pattern's number modulo P, then you actually do a comparison. Okay, so that could be, in the worst case, this can be bad, because you can get collisions. But it's going to turn out, we're going to see now why this isn't bad. Okay, so let's suppose that, okay, the thing, if you actually find an occurrence, if there is, say, 0, 3, 0, and there's a 0, 3, 0 here, it's the same number. So when you do mod P, it's the same. So if you have x mod P and x mod P, it gives you the same number. So you're going to find, you're going to say, oh, this looks like it could be this. I get the same number mod P. And then you do this comparison. Actually, you only do the comparison if you're paranoid. Frequently, if you do this right and you say, yeah, the chances of getting a collision, of getting a false positive, I'm just going to assume that the number was there. So sometimes for some applications you actually check, and for some applications you just assume that you're lucky. So for example, the worst case is still pretty bad, because, for example, if the text is all A's and the pattern is all A's, then at every position you're going to get a hit. And then if you go through and check character by character naively, you're actually also going to use MN time. You can make it a bit better. I mean, in the worst case, you can do it in linear time. So let's just see for a second how much time I have. 19 minutes. I don't actually know how much time I've used in this lecture. So the cool thing is, so what do? You say, okay, for I equals, so let's say that x equals p as a number. Oh no, p is a terrible choice. This is a little p as a prime. Let's say this is q. P mod q, where p is the pattern, viewed as a number. And then for I equals 1 to n minus m plus 1, if t I to I plus m minus 1. So this is, remember, this is p viewed as a number. So in base 255, if you want to consider ASCII. And this is also t, this substring of t viewed as a number. Mod q is equal to p mod q is equal to x, which is p mod q. Yeah, actually, I can fit that on the same line then. Then check if t I equals I plus p. So either you check this, maybe you check this, or maybe you just hope, and then you say, if so, print I. And if n4. Okay, so because you chose p, then these numbers don't get too big. This takes linear time as long as you don't get too many false positives. As long as you don't get too many things that hash to the same value as p mod q. Okay, so why is this not a problem? Generally, why can you sort of, why does this work? So the idea is, what is the probability t I to I plus m minus 1 is not equal to p, but t I plus m minus 1 mod q is equal to p mod q. Okay? Yeah, and also this is again, q is now the name of our prime, because otherwise I have to say lowercase p and uppercase p and lowercase p and uppercase p, and that would just be super annoying. So also, in order to make this a little bit easier, let's talk about p viewed as a number, which is x. Oh no, x was, yeah, p viewed as a number. So p can be a number, but I don't want to be writing this. So let's give this a name. Let's call this something. What can we call it? Let's call it S. What is the probability this substring? Let's call this S. S, which is equal to this substring of t, is not equal to p, but S mod q is equal to p mod q. Okay? So remember, we're viewing everything as numbers. So we're saying, what is the chance that this number is, these two numbers are not equal, but they are congruent to each other mod q. So, well, if S is congruent to P mod Q, so this just means that mod Q they're the same, then S minus P is congruent to 0 mod Q. Okay, so then their difference is a multiple of Q. Okay? Now, suppose, now this gets into a bit of like nasty statisticky stuff, but suppose we just consider a particular substring of T of length M. So some particular S. Now remember, we chose Q pseudo-randomly in that range. So say uniformly at random, if we could actually do things uniformly at random, and we didn't have to rely on pseudo-random number generators. So this is a particular number, S minus P. We fixed this substring of T, and P is fixed. So what's the chance that we've chosen a Q that divides this number? Well, how many prime factors can this number have? Okay. So how many distinct prime factors can a number have? Because we want to think, okay, so there's this fixed number, and we've chosen a prime from some big range, and that prime divides this number. Well, if the prime is bigger than the number, then bigger than this difference, then it doesn't divide it. So okay, we can ignore that. So the idea is, how big can this difference be? Well, not that big. I mean, S is, even if we view this as, if we're working in ASCII, it's going to be at most 2 to the 8 times m. So 2 to the 8 m. So this S, so this these two numbers, this difference is not, and P, wait, so P is, yeah, also, so S and P are as numbers less than 2 to the 8 m. So how many prime factors can there be in a number that's about 2 to the 8 m? Okay, so that's the size of S and P viewed as numbers. Well, not so many, right? Because if you think, how many primes can you multiply together until you get, how many distinct primes can you multiply together until you get something bigger than this? Well, if you're multiplying the smallest primes you can, in order to multiply as many of them as possible without going over this limit, then you would do 2 times 3 times 5 times 7 times 11 times 13. So this is okay, so the number of primes that divide this, that's going to be, that product is going to be bigger than 2 times 2 times 2 times 3 times 5 times 7 up to, for k numbers, is bigger than 2 times 2 times 2 times 2 times 2 k times. So that means that the number of primes is at most logarithmic. It's actually smaller than that, quite a bit smaller, but I don't want to prove it. So what you get is that this number, how many factors can it have? It's got some multiple of m, like 8. It's got, because the log of this is like 8m, so it's got about, so it's got something like m, order m distinct prime factors. And Q was chosen in this range, and there are a lot of primes in here. So there's actually, I forget what the name is, the prime number, prime distribution. No, I mean the fundamental theorem of arithmetic is that everything has a prime factorization. It says that the number of primes is basically n over log n in a range of size u. It's like u over log u, u over ln u, I think. So there are a lot of primes in here, and there are not so many distinct primes that divide this. So actually the chances of picking one of those primes from this range is very, very small. So it's okay. I won't go through any more math because we're probably running out of time. And I want to get to this last magic trick. So that's why you can actually say that, okay, if you do this properly, the chances of getting a false positive are billions to 1. Okay? You can find out more online. It's hard to teach all of these pattern matching algorithms in one lecture. So that doesn't seem so cool. It does. I mean, it seems very cool, but it doesn't seem unbelievable. Okay, so I'm going to stop this, and then I'm going to do just 10 minutes on why. Actually, have I been standing in the way of the board at the time? Here, if you want to see this, this is what it looks like. This is why I need to have this to see the screen, because otherwise I can't see when I'm blocking the board. But okay, so I'm going to stop this, and I'm going to do like 10 minutes on why you can use Karp-Rabin to do something you would normally think you couldn't do. Okay, please bear with me. And then I'll add up how much time I actually used, and